That's great. So to begin with, fine. So I welcome you all to today's session where we revisit the memory addressing concept. It's very, very important and hence we spend a lot of time on it. The last couple of classes we were discussing memory addressing. Now what we will do is we will try to solve some problems. Means you will be solving couple of problems on memory addressing, and if you face any problem, means we will see how many of you have solved and how many of you got correct answer, all those things. And if something goes wrong, then again we will solve it. We are not in a hurry. Our first year is not yet started. We have a lot of time. But whatever we learn perfectly, right? So whatever concepts we are trying to understand, we need to understand them properly and perfectly. And to cross check our understanding of memory addressing, we will solve a couple of problems. I'll be writing the questions here. Please, I requested you to maintain a small book, right? If not, at least today onwards, please maintain a book, and in that book, please note down important points. And now, please solve couple of problems one by one. So first, I'll write the questions here. Okay. The topic is memory addressing. So there are two steps in it, right? First, you have to divide the main memory into memory locations or memory words called as pieces. Pieces is a non-technical word. Then you have to generate addresses for every memory location. Inside every memory location, how many bytes you are going to get, you have to find it out. And for every byte, you should give an address. So question number one. In this question, the main memory is 4 GB, 4 gigabyte, and processor is 32-bit processor. So I want you people to find total number of number of address bits. So not only total number of address bits, you have to find this. Total number includes what? Includes the address bits which are required to address every byte, right? So like 31 address for 31-bit binary address to reach to a memory location. Another 2 bits we used to access a particular byte in that memory location. 31 plus 2, 33 was the answer in our previous question, right? In our previous example. So that total I want. So this is question number one. And question number two, my main memory is 16 GB and my processor capacity is 64-bit. So again, how many total number of address bits I need? I have to calculate. So these are the two problems. We have time, right? It is not a race. I'm not looking for who will do it first, who will do it last. I want you to understand the concept and I want you to generate the address properly. So question one, question two. I hope the question is clear. Please solve them and please do respond in the chat box, and we do have a discussion on this one. Question is displayed on the screen. Note down the question. Okay, never urgent. Okay. Right. The question is simple. Main memory is 4 GB, processor is 32-bit. Question number 1. 16 GB and 64-bit in question number 2. We started getting answers. 30 bits. Rohit, this is for first one, right? Question 1, 30 bits is one answer. Did anybody got any other answer? While typing, please mention question number. Varshini says, acha. Question number 1, 32 bits. Jashwant. Question number 2, 64 bits. 64. Question 1 is 2 power 30. See, answer can't be 2 power 30. Answer will be like 30, 31, 32 like that. 2 power 30, 2 power 31. Means 30 and 31 is the answer, Lakshmi Prasanna. Number of binary digits. Number of bits are 30 bits, 31 bits. Okay. Akshara also says the answer is 30 and 31. Okay. We'll check. We will check. Any other answer? We'll see what people will type. 32 and 34, we got a different answer now from Nivas. Interesting. Interesting. We will see when we get multiple answers. We have to see which one is correct. So that's interesting. Second one, 34, Srinivas says. Out of 36, I think around 10, 12 students have responded. What about remaining students? Varsha says 32 and 34. 32 and 34. I think most of the people who have answered, they said 32 and 34. That's great. 30 and 31, Muskan. Okay, we'll check. 30, 31, Vaishali. Prashant also says 30, 31. Let me check. Any other answers? $32 for first one. Okay. Fine. So let us solve this and we will see what answer, what is the correct answer that we will see. So question number 1, 4 GB and 32 bit, right? So friends, Q1 RAM is 4 GB, processor is 32 bit. So you know very well, first of all, your main memory should be divided into pieces of uniform size. And the division is based on your processor capability. So it should be divided into pieces. What is the size of each piece? That is dependent on CPU. So what is the capacity of my CPU? That will decide. My CPU capacity is 32 bit in this example. It means each piece is 32 bit, 32, 32, 32 like that. These are all 32 bit slices. Now, how many such slices I will get? How many memory locations I will get? First of all, I need to calculate these number of locations. How many memory locations I'll get? Number of memory locations. Number of memory locations is equal to total amount of memory divided by size of each location. Total amount of memory is 4 GB. Size of each location. What is the size of each location? It depends on your CPU's capability. How much your CPU can process at a time. Maximum is 32 bit. So size of the processor decides size of each memory location. It is 32 bit. So friends, 4 GB. 4 can be written as 2 power 2. Giga means 2 power 30. You know the relationship between capital B and small b. You know very well. 1 byte is 8 bits. Capital B is byte, small b is bit. So I can write 1 byte as 8 can be written as 2 power 3, small b as it is. So what is the relationship between byte and bit? 2 power 3, small b. 1 byte is 2 power 3, small b. So this capital B can be written as 2 power 3, small b, divided by 32b. 32 can be written as 2 power 5, small b as it is. Small b got cancelled on either side. Then 2 power 2 plus 30 is 32 plus 3 is 35. 2 power 35 divided by 2 power 5. What will happen in this division? It will become 2 power 35 minus 5, 2 power 30. 2 power 30. So what do you mean by 2 power 30? Number of memory locations are 2 power 30. This number is there, no memory locations. These are 2 power 30 memory locations. And for every memory location, I should give a unique address, unique binary address. It means what? What do you mean by that? I need to generate unique binary codes for every memory location. How many memory locations we have? Just now we have calculated. We have 2 power 30 memory locations. Now we know a basic logic with n bits. With n bits. How many different binary codes can be generated? 2 power n binary codes can be generated. 2 power different binary codes can be generated. With 30 bits, how many binary codes can be generated? 2 power 30 binary codes can be generated. So if I use a 30-bit binary address, How many different binary codes I can generate? 2 power 30 different binary codes can be generated. How many memory locations we have? We have 2 power 30 memory locations. So if I use a 30-bit binary code, 0000 like this, 30 zeros to 30 ones, it will be sufficient, right? So I have 2 power 30 memory locations. If I use a 30-bit binary code, I'll get 2 power 30 different combinations. Is it clear? Is it clear why I'm using a 30-bit binary address? If I use a 30-bit binary address, 2 power 30 different binary codes can be generated. How many memory locations I have? 2 power 30 memory locations. So it is matching or not? For 2 power 30 memory locations, I should generate unique address, separate address for every location. When it is possible, if my binary code, if my address is a 30-bit binary code, then 2 power 30 different binary codes can be generated. Each binary code will be given as address to one memory location. So is it clear? Is it clear to everyone? Once again, I am asking, is it clear to everyone? Please respond. Please do respond. Because tomorrow in quiz, I may ask this kind of questions again. I want every student to solve this properly, right? Then I'll be satisfied. Now please observe. I came to a conclusion like I need a 30-bit address, but you know very well what is the size of each location. How much is this one? 32-bit, 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 like that. Every location is 32-bit because we divided it such that every piece is 32-bit because my processor can process maximum of 32 bits. Now 32-bit means how many bytes? 32-bit means how many bytes? 88 bits together is 1 byte. So 32 bits means divide by 8, you will get 4 bytes, sir. So what do you mean by that? Meaning is in each row here I'll get 4 bytes. Means total row is 32 bit, right? So this is 8. This is another 8, another 8, another 8. Total 32. So in each row, we have 32 bit. So in the second row also, I have 32 bit. In third row also, I have 32 bit. Like that, in every row, I have 32 bit. I need to divide this 32 bit into 4 bytes. Obviously, 32 bits can be treated as 4 bytes. Why we are talking in terms of byte is, if your CPU is a 32-bit CPU, it can process 32 bits at a time. That is maximum. But how much minimum it can ask? What is the smallest unit of memory that can be accessed during a program execution? Means it is 1 byte. Means for every byte you should generate an address. For every byte you should generate an address. So if you use this 30-bit binary address, where you can reach, if I say 30 zeros, 30 zeros represent which memory location? First memory location. 30 ones represent which memory location? The last memory location. Yes or no? Now what I want in that first memory location, for example, my required data is sitting here. Let us say A. This is the data I want. Where is A located? It is located in first memory location. But first memory location, again, there are 4 partitions in it. There are 4 bytes in it. So with 30-bit binary code, I can reach to a memory location. That's it. With a 30-bit binary code, in this example, I can reach to a given memory location. It can be first, second, third, fourth, or last, whatever it is. But in that, which byte you want, means again, for that, you need to generate addresses. In each row, how many partitions we have, how many cells we have? We have 4 cells. We call them as first byte. We always go in this direction, right? So this is first byte, second byte, third byte, fourth byte. But for every byte also, you should give address. If there are 4 different locations for which I need to generate address, how many bit binary code I need? 2-bit binary code is enough because 2 power 2 is 4. 2 power 2 is 4. So apart from that 30-bit address, another 2 bits I use. I call this one as 00, 01, 10, 11. So if you look at this one, 30-bit address will take me to a memory location. Another 2 bits will tell me in that memory location which cell you want. So the answer is 30 plus 2, 32-bit binary address. I also told you there should not be any confusion. In every row, the same combination can be repeated. Every row, same combination can be repeated. So don't think that this cell is also 00. This cell's address is also 00. Don't think that why address has been repeated. No, no. Total address you have to see. What is the address of this location, sir? It is 30 zeros plus 00. So what is the address of this one? 32 zeros. Whereas what is the address of this one? 31s plus 00. So like that, every byte will get a unique address. No doubt in that. So final answer is 32-bit. There are few students who got 30-bit answer. I understand that they have only calculated the number of bits required to address a single memory location. In that memory location, how many bytes are there? And for every byte, you should generate an address. That part they have not done. Now, those who got 30 as the answer, for them, there was a misunderstanding. Those who got 32-bit as the answer, they have done it clearly. So I'm asking the students who have given me answer as 30, I'm asking them, is it clear now? Kindly respond. Please respond, sir. Lakshmi Prasanna, yeah. Shall we solve the second one now? So the final answer is 32, but you should understand it is 30 plus 2, 32. 30 for memory location, 2 bits for a particular byte in a memory location, right? Let's move on. What was our next question? Second question was, we had a 16 GB RAM and processor was 64-bit. So what is step 1? Step 1, your main memory will be divided. It's looking very odd. So we know very well, main memory will be divided into pieces. Now in this example, what is the size of each piece, sir? Please respond in the chat box. In this example, what is the size of each piece? So we have to calculate number of memory locations. What is the size of each piece? In this question, what is the size of each piece? Size of memory location, size of each memory word is decided based on your CPU capability. Yes, you are all correct. 64-bit. So I'll be dividing my 16 GB RAM into pieces of size 64-bit each. So let us do the division now. So it is 16 GB divided by 64-bit. 16 can be written as 2 power 4. Giga can be written as 2 power 30. Byte can be written as 2 power 3 small b divided by 64 is nothing but 2 power 6 and small b as it is, b and b got cancelled. Now it is 2 power 4 plus 30, 34, 34 plus 3, 2 power 37 divided by 2 power 6. It will become 2 power 37 minus 6, 2 power 31. How many memory locations we have? Number of memory locations are 2 power 31. So what should be the number of bits, or how many number of bits I need to give unique address to every memory location? Each memory location is 64-bit. That is different. But how many memory locations we got? We got 2 power 31 memory locations. For every memory location, I should give a unique address, different address. If I use binary code, then how many bits I need? Same formula. If I use n bit, 2 power n combinations I'll get. If I use 31-bit address, 31-bit binary code, 2 power 31 combinations I'll get. How many memory locations I have? 2 power 31. So I'll be using a 31-bit binary code. With 31-bit binary code, what will happen? I will get 2 power 31 different memory locations. So the answer is not yet complete. 31 we got. Now, what is the size of each piece, sir? This is 64-bit, 64-bit, 64-bit. Every piece is 64-bit. 64-bit means how many bytes we will get? 32 means 4 bytes. 64 means how many bytes we will get? 64 divided by 8. We will get 8 bytes, means 8 pieces here I'll get. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So I need to have one more. So total now, if you observe, we have 8 pieces, right? It's not looking nice. So 1, 2, 3, 4, 5, 6, 7, 8. So total 8 pieces. Since every memory location is same 64-bit, I'll get 8 pieces everywhere. That's the reason this line will continue. So every memory location, I'll get 8 pieces, right? Oh my God. Please forgive me for this very odd drawing. Just focus on the concept. So in each row, in each memory location, how many cells we got? How many location? How many bytes we got? We got 8 cells. We count in this direction, right to left. First, second, third, fourth, fifth, sixth, seventh, 8. So 8 locations we got. Now for 8 cells, for 8 bytes, I should generate a unique address now. So for 8 cells, if I use a 2-bit binary code, how many combinations I'll get? 2 power 2. 2 power 2 means what? 4. But how many addresses, how many cells I have? 8. So 2-bit is not sufficient. Suppose if I use 3-bit, how many combinations I'll get? 2 power 3, which is 8. Means I need a 3-bit address here to address each byte. So let me call this one as 0, 0, 0, 0, 0, 1, 0, 1, 0, 011, 100, 101, 110, and 111. So another 3 bits I need to access a particular byte in the main memory. For example, please observe this. Suppose in this location, I have some data which I need to access. So what is the address of this location? It is 31 zeros followed by 011. Suppose if my data is here in this last location, then what will be the address of this last byte? 31 ones followed by 111. Am I correct? 31 ones followed by 111. So finally, what is the answer? 31 bits for my memory location, another 3 bits for a particular byte. 34 is the answer. I'm very happy that most of you have done it properly. Some students had a little bit of confusion. Now I hope the confusion is clear. There is no confusion in this particular most important topic. So I would like to hear from you, is the concept of memory addressing fully understood to everyone? Kindly respond in the chat box. Yeah, you're right, Jaswant, Varshini. Yeah. Everyone, please just put a message. If you have any doubt, please don't hesitate to ask. Everyone, please respond. Very few responses I'm seeing. Jaswant, Muskan, Nikhil, Akshara, Lakshmi Prasanna. Fine. Thank you. Thank you for responding. That's great. Now let's move on. Let us move on. We will discuss couple of important aspects related to binary number system. We have already discussed a few things in binary number system. So how many digits are there in binary number system? Only 2 digits. Only 2 values. What are they? 0 and 1. Only 2 values. What is the base of binary number system? Base depends on number of values in the number system. So base is 2. Okay. Fine. How do we convert a decimal number to binary? There are 2 methods. One is 8421 code. Another method is LCM. 8421 code we have already discussed. Am I correct? We have discussed 8421 code already. What is 8421 code? Let us revisit. Let us try to understand 8421 code. 8421 code is based on the face value of every digit, every position in the binary number system. The first, numbers we give positions, values from right to left. In decimal number system, we call it as ones, tens, hundreds, thousands, like that. Similarly, here, what we will do is, instead of saying ones, tens, hundreds, 10 power 0, 10 power 1, that is the face value of every digit in decimal number system. Whereas in binary, it is 2 power 0. What is the value of 2 power 0? Anything power 0 is 1. So 2 power 0 is 1. 2 power 1 is 2. 2 power 2 is 4. 2 power 3 is 8. 2 power 3 is 8. 2 power 4, 16. 2 power 5, 32. Like that it will continue, sir. 2 power 6, 64. 2 power 7, 128. 2 power 8, 256. Like that it will continue. It is infinite sequence, from right to left. So what is 8421 code means? What we will do is, suppose I need binary code, decimal to binary conversion, right? Suppose there is a decimal number called as 11. What is the binary code of 11? You apply 8421 code. 8. Now, based on the position, what are the positions that can be added to get 11? 8 plus 4, it is 12. It is going beyond that. So I can't add 8 and 4. 8 plus 2 is 10. 10 plus 1 is 11. So what are the positions that can be added to get 11? 8, 2 and 1. In those positions, write 1. In remaining positions, write 0. This is the binary code of 11. What is binary code of 11? 1011. So we will write like this: 11 base 10, 1011 base 2, decimal and binary. Okay. Now similarly, what is the binary code of 15 base 10? What is binary code? Again, you apply 8421 code. 8 plus 4 is 12, 12 plus 2 is 14, 14 plus 1 is 15. Means I need 8, I need to add 4, 2, all are required. So the answer is 1111. 15 can be written as 1111 base. Sorry, this is base 2, right? Base 2. So this is the binary code of 15. Okay. Now same calculation can be done using another method called as LCM method. What was our first number? 11, right? This is the second method. 2 5s are 10. So why I am dividing 11 with 10? Because decimal to binary conversion I am doing, and in the binary number the base is 2. So I am dividing it with 2. So 2 5s are 10. What is the remainder? Remainder is 1. 2 2s are 4. What is the remainder? Remainder is 1. 2 1s are 2. What is the remainder? Remainder is 0. Remember, after doing LCM, you have to collect the answer from bottom to top. This is important, my dear. Bottom to top. So what is the answer? 1 0 1 1. This is binary form of 11. Right? Remember, answer need to be collected from bottom to top. 15. The other example, 2 7s are 14, 1 carry, 2 3s are 6, 1, then 2 1s are 2, remainder is 1. Collect the answer in the reverse direction. It is 1 1 1. Maybe in this case, if you collect the answer from top to bottom, you are getting the same answer. But remember, you need to collect the answer from bottom to top only. Right? Now, you can apply any method, either 8421 code method or LCM method. Can you convert following decimal numbers to binary? So some questions for you. I want 15 base 10. What is the binary form? 16 base 10. What is the answer? 32 base 10. What is the answer? Then 100 base 10. What is the answer? That's it. These 4 numbers. So please calculate what are the binary codes, binary numbers of following decimal inputs. 15. What is the binary code? Just now we have calculated 15, 16, 32, 100. I want you to solve this, convert decimal to binary. Give me the answers in the chat box. 15, 16, 32, 100. That's great. For 15, it can't be 1 followed by multiple zeros. 15 is all 4 ones. Acha, second one is 1,000. That's great. That's great. Intentionally, I asked this conversion because there is an important point which I wanted to teach you. So what is the binary code of 15? It is 1, 1, 1, 1. Binary code of 16 is 1 followed by 4 zeros. How many number of bits we got? For 15, 4 bits are enough. For 16, I need 5 bits. For 32, what is the binary code of 32? 2 16s, remainder is 0. 2 8s, remainder is 0. 2 4s, remainder is 0. 2 2s, remainder is 0. 2 1s, remainder is 0. Collect the answer in reverse direction. 1 0 0 0 0 0. 1 2 3 4 5, right? 3 5 base 2. So it is 1 followed by 5 zeros. So total 6 bits I need to represent 32. For 100, what is the binary code we got? I'll apply 8421 code here. 16, 32, 64. 64 plus 32, 4 plus 2, it is 6. And 6 plus 3, 9. So 64 plus 32 is 96. This is plus 4 is 100. So the answer is, am I correct? 1 1 0 0 1 0 0. 3 plus 4, 7 bits I need. So is the binary code for 100 correct, sir? 4 plus 2, 6, 6 plus 3, 9. 64 and 32, if I add, I'll get 96. Another 4, it is 100. So in remaining positions, I kept zeros. Now, whatever is comfortable and convenient for you, that particular method, either 8421 code or LCM, you can apply. So till this point, is it clear how conversion is done? Yeah, for 100, 1100, 100. That's great. Fine. Now, if till this point, if the conversion is clear, either by 8421 code or LCM method, we need to identify an important point, and based on this important point, 2 important objective type questions will be discussed now. 2 important points I am going to share with you. These 2 important points will come as questions in many places. It can be in interviews, it can be in competitive exams like GATE, right? And maybe even in recruitment exams, in your placement drives. Some companies, they do a multiple choice round as round one. Many companies do a MCQ round as first round. Even in your recruitment, this kind of question will come. So please listen carefully. I'm going to explain you a very important question. Two MCQs will come based on this point. Please observe. Okay. With 2 bits, how many different binary codes I'll get, sir? With 2 bits. How many different binary codes I'll get? 2 power 2. 2 power 2 different binary codes. 4 binary codes I will get. You know this. Now let us write those binary codes. 0, 0, 0, 1, 1, 0, 1, 1. This is the binary code. In the decimal, what is the equivalent decimal value for this binary code? What is the equivalent decimal value? 0, 0 means what? 0. 0, 1. Convert binary to decimal, sir. Please convert binary to decimal. How do we convert binary to decimal? Multiplication. Decimal to binary is division. Binary to decimal is either multiplication or 8421 code. 8421. How many bits I have? Only 2 bits. So 84 is not required. Only 2 bits. 0, 0 means what is the decimal value? 0. 0, 1. Which bit is highlighted? Only this bit is highlighted. Decimal value is 1. 1, 0. What is the decimal value? 2 plus 1. Am I adding both? No, this is 0, so I am not considering it. So it is, this bit is 1. This bit is 1 means what is the answer? 2 is the answer. If this both bits are 1, it is 2 plus 1. Answer is 3. Using 8421 code, I can generate equivalent decimal code, or I can do a multiplication method. What is multiplication? For example, let me take 0, 0. This is binary, right? How do I generate equivalent decimal code? Multiplication method. What I'll do, this is first bit, right? 0 into, what is the position of this one? First bit means 2 power 0 plus 0 into 2 power 1. 0 into anything is 0. 0 into anything is 0. Final answer is 0. This is decimal value, right? Decimal 0. Now similarly for 0, 1, what is the answer? 1 into 2 power 0 plus 0 into 2 power 1. Anything power 0 is 1. 1 into 1 is 1 plus 2 power 1 is 2, but 2 into 0 is 0. Answer is 1. This is decimal value, sir. Decimal 1. Means 0, 1 in the binary form is nothing but a decimal 1. Similarly, you please calculate for 1, 0. First bit 0 into 2 power 0 plus 1 into 2 power 1. 0 into 2 power 0 is 0 because 0 into anything is 0. 1 into 2 power 1. 2 power 1 is 2. 2 into 1 is 2. 2 plus 0. Answer is 2. So what is 1, 0? 2. What is 1, 1? What is 1, 1? Just now we have calculated. Let me do it again. 1, 1. 1 into 2 power 0. First right to left, sir. Plus 1 into 2 power 1. 2 power 0 is 1. 1 into 1 it is 1 plus 2 power 1 is 2. 2 into 1, 2. 2 plus 1, 3 is the answer. So 0, 0 means 0. 0, 1 means 1. 1, 0 means 2. 1, 1 means 3. Okay. This is point to be noted. Now let us move on. Let us move on. Similarly, with 3 bits, How many different combinations I'll get? 2 power 3 binary combinations. You know that. With 3 bits, I'll get 2 power 3. What are they? Let me write it in a proper order. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, double 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, triple 1. You will get 8 combinations. I wrote those 8 combinations here. Now equivalent decimal code we will write. 000 means 0. 001. You can calculate it. It apply 8421 code or multiplication method. 010 means 2. This is 4. No, 8421 code means 421. So add all these. Is there any 1 in this binary code? There is no 1. We have to add the face value of the bits where there is a 1. Is there any 1 in the first one? There is no 1, all zeros. So decimal value is also 0. Is there any 1 in this one? Yes, there is a 1, but only one place there is a 1. What is that one place? Its face value is 1. So answer is 1. Again, in this one, is there any 1 in this binary code? Yes, there is a 1, but there is only one 1. There is only one binary 1 is there. In which position? Position number 2. Answer is 2. Similarly, 0, double 1. 1 and 1. Two ones are there. In which position? 2 and 1. Add them. 2 plus 1. This is 3. Similarly, in this binary code 100, where is a 1? Only one is present. Where it is? In this particular location. What is the face value of this third position? Face value is 4. So decimal value is 4. This is 4 and 1. 4 plus 1 is 5. This is 4 plus 2. Wherever ones are there, those positions I am adding. Ones are there at 4 and 2. 4 plus 2 is 6. All ones are there. 4 plus 2 plus 1, it is 7. So when we had only 2 bits, it was like this. 0, 0, 0, 0, 1, 2, 3. The most important point to be noted is, with 2 bits, how many combinations you got? With 2 bits, you got 2 power 2 combinations. That is but nothing but 4 combinations or 4 binary codes. 4 binary codes. But when you have converted them into decimal, what is the biggest number you could have represented with 2 bits? With 2 bits, when I converted them into decimal, what is the biggest number I got? 3. Right? And with 3 bits, how many combinations we will get? With 3 bits, we will get 2 power 3 combinations, 8 different binary codes. But what is the biggest value I got? 7. So what is the point to be noted is, this is an important formula, sir. With the n bits, you will get 2 power n binary codes. Or you can say, with n bits, you can represent 2 power n different numbers. With n bits, the biggest possible number is 2 power n minus 1 is the largest number that can be represented. Okay, this is an important formula, sir. For example, with 3 bits, how many combinations we will get? 8 combinations. Just now we have seen with 3 bits, we have written 8 combinations. What is the biggest possible number we got? We got 7. What is 7? Can I write 7 as 2 power n minus 1? So suppose if n is 3 bits, n is 3 bits, 2 power 3 is 8 numbers. 8 numbers. Did we get 8 numbers? Yes, from 000 to 111. with 3 bits, what is the biggest possible number? 2 power 3 minus 1, which is 8 minus 1. 7 is the largest number that can be represented. Now tell me for 4 bits, what is the largest possible number? What is the largest possible number? With 4 bits, what is the largest possible number? With 4 bits, the largest possible number is 2 power 4 minus 1, 15. That's great. With 4 bits, the largest possible number is 2 power 4 minus 1, 15. So remember these two things. With n bits, how many different numbers can be represented? The answer is 2 power n. And what is the biggest number that can be represented? Answer is 2 power n minus 1. This is a very, very important formula, which is very useful down the line in your programming journey. So before we wind up, quickly give me a response, feedback in the chat box, whether today's class was very much clear or not. Please let me know quickly in the chat box. Everyone, please respond. That's great. Thank you. Thank you very much. Tomorrow we will have a quiz. Thank you, everyone.